So I'm going to talk about high-performance computing. My area of research is in developing algorithms and software that run on the fastest computers. And I'd like to begin by taking a look at science and how things are done. So traditionally, scientific and engineering has relied on theory and experimentation. So theory is a paper and pencil process where we go and try to look at new ideas. We think about that didn't work quite as well as predicted. And we think about experiments as testing the theory. We build something. We may, in fact, go back and change the theory based on the experiments. There's an interplay that takes place between that. And today we're using computational science as a third, I'll call it pillar, to supplement the ideas used in theory and physical experiments. So we use high-performance computers to simulate physical phenomena that are based on these physical laws and numerical methods. And we look at high-performance computers to help us with that process. So we can think of these high-performance computers as sophisticated scientific instruments, sort of like the Webb telescope, but only for a much more general set of topics. So computational science fits into that. And HPC really involves aggregating the computer power that we have today to solve these complex problems with high-speed computers. Given that we have tremendous advances that happen as a result of using these machines, so we use them for clean energy, for looking at the power grid and improving it, for climate change, for cancer research, looking at advanced materials, and also for catalysis. So those are just some of the ways in which we use it. And we've seen this incredible change take place in our computing devices. You know, we have, when I started computing about 50 years ago, the computer that I was using was a Cray computer. Cray is based on vector instructions. That's how it got a lot of its performance. And after that came parallel computers and distributed systems. And after that came the rise of GPUs, or graphical processing units, which we use really to extract and to boost the performance of the floating point operations. And it turns into clouds and high-performance computing. So we've seen this transition from vector to shared memory parallel computers to distributed to massively parallel to clusters. And today we have this accelerated computing, which uses GPUs and conventional computers. And on the horizon, of course, is the potential for doing quantum computing. And AI is really augmenting all of that computation to help us understand things better. I've been involved in algorithms and software, and those algorithms and software have really followed that trend, that technology that's been improving, trying to design software that runs effectively on those machines. The one thing I will point out is that the evolving software and algorithms always follow the hardware developments that take place. So there's a lag in time before we can actually use the machines at their potential. And that's because of having to rework the algorithms and redefine the software that runs on those machines. This is a plot of the fastest computer over the past 36 years. Today, the fastest computer is a machine at Lawrence Livermore National Lab. It runs at 1.8 exaflops. So that's 1.8 times 10 to the 18 floating point operations per second. So a floating point operation is 64 bits in this context. So 16 decimal digit adds or multiplies. So 1.8 exaflops, I have a hard time getting my hands around that number. So an exaflop, that's the number of seconds since the Big Bang is measured by 10 to the 18 seconds. So that's sort of the magnitude that we have here of this number. And back in 1993, the fastest computer was a machine at Los Alamos National Lab, and it ran this benchmark at about 140 gigaflops. And today my laptop can outpace that machine that was used back in that time. So incredible changes over a very short period of time. So HPC is really synonymous with numerical modeling and generative AI. The deductive world of physics-based mathematical models is increasingly being augmented today with the inductive world of surrogate models that are created by generative AI. These hybrid models are rapidly expanding a rich parameter set of spaces and taking the modeling much further. So weather modeling is a good example of that. So traditionally, weather modeling has been done by numerical models. Today, with the analysis of 40 years of data, the AI can really be in a position to predict the 10-day forecast in seconds rather than in hours for the numerical methods, and do it in a way that's actually much more accurate than those numerical models. As an example, the ECMWF, the European Center, is switching over to use AI to help with its productive things. And as Tony mentioned, protein folding through AlphaFold and Rosetta Fold really have increased the accurate prediction of these 3D structures, and that gave way to a Nobel Prize a couple of years ago.
Thank you, Jack. Time's out.
Time's up. Okay. So many other things can be done with AI, and I just want to point out that today, we have this constantly changing world from scalar to vector to distributed to accelerated computing with using mixed precision today. Again, hardware advances quickly, algorithms and software follow those advances, and I think I'll have to end there because Tony's about to cut me off.
Thank you very much. Okay. So next speaker is Bob Tarjan. I looked up a citation for his 1986 Turing Award. It says 4 fundamental achievements in the design and analysis of algorithms and data structures. His work, recognized for its profound impact on computer science, includes developing efficient algorithms for graph problems and pioneering data structure. So that's the full quote. Just a personal note. I was in his class at Stanford. I just reminded him when I was a graduate student, and I follow his footsteps from Caltech to Stanford in the same field, in the same department. So Bob, please.
Thank you. It's a great pleasure to be here and an honor. AI systems, as we know them, hallucinate. I have some personal experience of this. I attended a similar meeting, and in preparation, the organizers prepared a CV for me, which gave me 2 awards that I never received. I asked them about it. ChatGPT prepared the CV. So these systems hallucinate. This is important to think about. I'll come back to that in a minute. My field of research is design and analysis of data structures and graph algorithms. It's some plumbing layer in computation. Let me begin with a few observations about computer science. Unlike physics and mathematics, computer science is a very young field. The work that I do in algorithms and data structures started more or less in World War II, or you can give examples before that. So that's 60 years during which we've developed beautiful, theoretically efficient algorithms and data structures, but computer science is still a young field. We've often settled for the first good enough solution, but it may not be the best. The design space is rich, and as computers get faster and memories get bigger, the design space only gets larger, and we need to explore the enlarged design space. So my objective in research is to develop and analyze what I'll call reference algorithms. It's really mathematics. Paul Erdős, who was a well-known mathematician, had this idea of proofs from the book. This is the book in the sky. We can think of algorithms in the same way. We want to develop algorithms that are as simple as possible with provable resource bounds that are efficient in practice. Einstein supposedly said, make everything as simple as possible, but not simpler. So that is the goal here. So let me just mention some examples of problems I worked on having to do with graphs, which are points and line segments connecting the points. So a simple question is, can we embed a graph in the plane so that no two edges cross? This is the planarity problem. This is important in circuit layout because if you have connections in the circuit that overlap, you're going to get short circuits. Together with John Hopcroft, who was my co-winner of the Turing Award, we came up with a linear time algorithm for testing planarity based upon depth-first search and some data structures. Another example, specifically to data structures, was an analysis of a very simple algorithm that allows you to keep track of connected components in graphs. Think of the Facebook friendship graph. Are two people connected by a path of friends? And what happens when we add new friendship relations? How do we keep track of the connected components on a graph of billions and billions of vertices? We want to have a data structure that allows us to add edges rapidly and update the graph. So there's a beautiful and simple algorithm for doing this, which seems to run in constant time per operation, but it turns out not. This algorithm is simple, the analysis is complicated, and the analysis gives a solution that's the inverse of Ackermann's function, which I won't describe, but is a function invented by logicians for a completely different purpose, and it grows incredibly rapidly. It grows so rapidly that the inverse function you can't tell the difference between constant and this very slowly growing function by any kind of experiment. The most recent project I've been involved in is shortest path algorithms. You have experience with this with your favorite mapping application. You can compute the exact shortest path distance on a road network almost instantaneously on your cell phone. There's a lot of technology and algorithm design behind this, and recently we were able to prove that in a certain sense the fundamental algorithm in this area, Dijkstra's algorithm, is best possible in a very strong sense. What kind of tools are involved in this research? Finite mathematical tools, combinatorics, mathematical induction, logic, finite probability. Lots of interesting questions. What I tell my students, and what is really true, is asking the right question is more important than finding the answer. To be a really great researcher, you have to develop a certain kind of taste to identify those problems that are really crucial. Now, what is the role of AI here? It can't hallucinate. The kind of things that AI could help me in my research do are, first of all, provide rigor, fill in proof details, find missing cases, build counterexamples. Explore the proof space. I have a conjecture. Can the system prove this for me? Explore the design space. Can an AI invent new algorithms for certain kinds of problems? Going beyond this to more general questions.
30 seconds.
I'm almost done.
Okay, thank you.
Can AI explore the problems space? The whole same question you were asking. Can it come up with general relativity or quantum mechanics on its own? And I think all these questions are still open. Large language models are not the kind of AI tools that are needed to address these particular sorts of questions, but there are certainly mathematicians who are actively working to try to use AI tools to solve some of these problems. Thank you.
Thank you very much. Next speaker is Arieh Warshel. His 2013 Nobel Prize citation reads like this: for the development of multi-scale models for complex chemical systems. Now, in a way, this is close to what Jack talked about, scientific computing, but using on chemical and biological system. I've always known about his work, so please, Arieh, I don't know where you are.
Okay, thank you very much. And I will talk on the relationship between physically based simulation to AI. I will give several examples. My first example is trying to study enzyme design by massive use of computer simulation, where we have a lot of experience. We took the enzyme CAMP eliminase, which was refined by directed evolution, and we tried to see if we could reproduce the result of directed evolution in terms of the catalytic efficiency. The blue are the fastest enzymes, and after a lot of effort, which continue for many years, we found that we are in the range of the predicted directed evolution, of the observed directed evolution, but we are not good enough. And since I work in this field for like 40 years, I decided to try something else and move in desperation to AI. We use maximum entropy to try to see if it has any correlation with catalytic efficiency. And for several enzymes, we found very impressive correlation where the energy of maximum entropy is directly correlated with the catalytic power of different type of enzymes. And the catalytic power was not included in the learning process. So regardless of the reason why it worked, we were able to predict, at least in one case, naturally evolved enzyme which is faster in one step than what evolution did. So it's clearly some accomplishment of AI. We then tried on bioluminescence, where the enzymes in these creatures try to get to the most blue direction because the creatures live in water and you want to pass the visible range in water. And again, with maximum entropy, we found a very nice correlation which allow us to even suggest improving luciferase, which have large industrial application. Now, the most recent example, or almost the most recent, okay, we took kinesin, which is supposed to be here in the movie. Its work in one direction, and one of the puzzle is what makes kinesin and other myosins work only in one direction. We spent a lot of time trying to figure it out, and we discover that it's not due to any magic idea like power stroke, but actually to the rate determined step and the barrier for this step. And we studied it with many systems, but maybe the most impressive one, which is very recent, it was just published, was a kinesin-like system which has very strange feature. In some mutation, it's go forward, and in other mutation, it stop, and in other mutation, it goes backward. So first, we studied this system by physical-based simulation. We study the ADP release rate limiting step, and we look for the barrier, as you see. In some case, the barrier for the mutant is higher. In other step, it's lower. And in the last step, it just stops. So by physical simulation, we were able to understand why this is happening. And then we just play a little with AI, with maximum entropy, and we found that there is a nice correlation, not really good enough, but there is a nice correlation between the maximum entropy prediction to the directionality. In this case, we were overexcited, and we try to apply this to kinosine which are involved in heart disease, well, we were very successful with physical method to get the right directionality, but maximum entropy did not do too well.
Time's out.
Since I have, okay, so anyhow, this is not the end of the story, but several examples. Thank you very much.
Thank you. The next keynote speaker is Yurii Nesterov. He is the winner of the World Laureates Association Prize in Computer Science in 2023. He is an expert in optimization algorithms. He won that prize together with Nemirovsky. So the citation says, their work has sparked a revolution in the field, leading to the development of new algorithms that are more efficient and scalable. And I suspect these algorithms are used a lot in deep learning problems in the world. So please, yeah.
Okay, thank you very much for this opportunity to discuss artificial intelligence in this audience, but it seems everybody in this room understands this differently. Therefore, let me start maybe with general remarks. As you know, that in the last decades in the computer science, we observed a sequence of revolutions, like invention of personal computers, development of internet, and availability of big data models. Finally, we have seen maybe the most important event in the history of sciences, the birth of artificial intelligence. Its appearance was widely recognized in view of the remarkable success of neural networks. Intelligence. It was achieved by creating a system of sciences responsible for different facets of human activity. Note that the main tool for generating the new knowledge in all these sciences, maybe except math, is the verbal convincing reasoning. For artificial intelligence, this doesn't work. It accepts only the results of computation represented by numbers. Hence, we need to create a system of new sciences suitable for the needs of artificial intelligence. This is an extremely challenging task, and now we're only in the beginning of the process. We only start learning how this can be done efficiently. By analogy with human intelligence, it is clear that we need to create at least two things. The first one is the virtual reality, which is the main object of investigation of artificial intelligence. This reality should exist in the form of big databases accumulated in the powerful compute data centers. Creation of this part of the system is very expensive and time-consuming. Hence, comparison between different actors of this field is very reasonable. Note for the human intelligence, we get the surrounding reality, so-called the world of things, for free. The second element in this system is the artificial intelligence itself, the unit which must be able to generate specific answers or decisions requested by a human being. Its performance is achieved by a training process provided by the available database. At this phase, machine learning should be already involved, since it can endow us with an efficient training procedures. In principle, the education process shouldn't be too expensive. If we compute the total energy spent for development of intelligence of a human being, say for the period of 20 years, we get an upper estimate in 17 megawatt hours. In the current prices for electricity in Europe, this is less than 5,000 euros. But of course, the training algorithm for a human being and for artificial intelligence are totally different. The nature had millions of years for selecting the best procedure by the straightforward natural selections. For artificial intelligence, during the last decade, we just started verification of different strategies. Most of them are based on optimization models and employ the numerical optimization methods. However, we still lose several orders of magnitude in the guarantees for the required computational time. We hope that this is a temporary inefficiency, which will be eliminated by the further development of the field. This is the situation in machine learning right now. Coming back to the main topic of our discussion, I believe that artificial intelligence has indeed a considerable creative power. It can discover new links, structures, and properties of the investigated objects. But there is an essential difference with the conclusions of human intelligence. When a biologist investigates a certain object, say bird, the conclusions will be related to the real bird. However, the conclusion of artificial intelligence can be related only to a model of the bird which exists in the corresponding virtual reality. If the model is done correctly, then this conclusion can be used in the real life. If not, it could be a complete nonsense. To conclude, I would like to repeat that at this moment of development of artificial intelligence, it is highly desirable to establish cooperation of different partners for creating a detailed virtual model of the reality. This model can be used later for training different artificial experts, which will be educated for working in different domains. The creation of such experts should be relatively cheap. It can be done by different firms using the common database treated as a virtual reality model. Thank you.
Thank you very much. Thank you for finishing ahead of time. Thank you. Next speaker is Professor Omar Yaghi. He is the 2025 Nobel Laureate in Chemistry. His citation reads very simply for his pioneering development of metal-organic frameworks, MOFs. It reads like science fiction. It can be used to capture carbon and water from the air. I should add one personal note. He's now at the University of California, Berkeley. So I hope you agree. I was partially responsible for recruiting him to UCLA, but I'm not responsible for losing him to Berkeley. Thank you, Omar.
Thank you, Tony. Let me start by saying that making new chemical structures and new molecules is at the heart of science. And one of the biggest difficulties in making them is to make them in an ordered form, meaning to make them as crystals. So while sometimes, as we have done with MOFs, COFs, and other materials, it's easy now to make MOFs and COFs, but it's not so easy to crystallize them. It takes a student potentially a year to 2 years, maybe sometimes in the case of COFs, 3 years to make crystals of these materials. The reason crystals are important is because we want to characterize them on the atomic and molecular level using single crystal X-ray diffraction. And we also, in some applications, crystallinity or the order of the material is extremely important to its function, such as in the case of water harvesting from air. So let me just say that the interest in these materials lies in their ability to encompass tremendous amount of space, that in 1 gram of one of these structures, like maybe the size of a sugar cube, encompasses as much space as an entire football field. And recently, we've been able to even make them encompass space that is double a football field for each gram. So this exciting property makes them extremely important, various applications. In fact, hundreds of applications are being pursued right now in the community, and some of them dealing with water harvesting from air. This is where the structures are programmed to pluck out water from air and make concentrating the water into the pores. This is now becoming almost a commercialized product. It will be unveiled this year, a product that would produce almost 1,000 liters of water per day, every day for 6 to 7 years, with no energy input aside from ambient sunlight. So we've solved, let's say, the water harvesting problem. Now we can create water from thin air, and we can take CO2 out of the air. Why am I telling you this? Is because it has taken us 35 years to get here. And that's what makes AI so exciting to me. And so I'm going to give you 2 examples of how we've been using AI very effectively to accelerate not just discovery, but also the development of the devices that ultimately are commercialized. I call this field ametry, AI mixed with materials and mixed with chemistry. And ametry is about deploying AI tools to make them productively useful in chemistry and in making materials. I'll give you a simple example. This is, for the young people in the audience, this is familiar. For people like me, it's not so familiar. This is a long prompt given to ChatGPT. And basically, you're telling ChatGPT exactly what you're doing. You're saying you are a reticular chemist. That's like my brand of chemist, developing a particular cough. You have a robotic platform that will execute the experiment. Your taxes, conduct literature, whatever. You're giving it all the instructions, including actually creating a reference list and making sure that it does things accurately. And the idea here is that we wanted ChatGPT to give us the conditions under which to crystallize a specific cough that has been really difficult to crystallize. For 10 years, the whole community has been trying to crystallize this. And so it spit out a whole bunch of conditions that we ultimately put in a robot and put in the results of that data. So here is the experimental cycle. We take the conditions generated by ChatGPT, we do the experiment in the robot, solid dispensing, we do all these different things, and then we characterize by high throughput powder diffraction and put this results back into ChatGPT, okay? And so we did this cycle 3 times, and we were able to get not just one well that has high crystallinity, but we were able to make that crystallinity 3 times what the community has been trying to do for the last 10 years. So 3 times as crystalline. This is truly revolutionary for the way we're doing chemistry today. And so it has changed my entire group from just an experimental group into a group that blends AI with AI tools and LLMs. The other thing is that we've designed, right now, we are following these 3 cycles. One is a predictive cycle married to an experimental cycle, a synthesis cycle, and then the other one is a scaling cycle, which has to do with the application. And these 3 cycles work together. One feeds into the other. And the more frequently you go around these cycles, the better these machine learning models get. So when you adapt your machine learning algorithms to this kind of chemistry, what the students that are using these cycles can do is double the rate of discovery compared to students that are not using these machine learning algorithms. And so yes, we can make not just new compounds, but new compounds that experts in the field would not have anticipated. So can AI help us in speeding up discovery? Yes. Can it simplify the tasks and eliminate a lot of the trial and error that we chemists use to crystallize things? Yes. Will it get better? Yes. The more we use it, the better it will get. And I think we are in the middle of a revolution transforming chemistry by blending it with AI.
Thank you.
Thank you.